My name's Rijnard and Tonder. I'm from Stellenbosch University. If you need a reference for that, it's about an hour's drive from Cape Town in South Africa. And so this was work that I did during my master's. And the motivation really was just, well, we have USB, it's ubiquitous, and there's some high security kind of impacting bugs in drivers that were discovered 2013, 2012. And what you really want to do is just get into this USB port. How can we kind of get into the data that's flowing across on that channel? And it's kind of difficult to explore. If you're interested in just finding driver bugs, for example, pure software solutions are difficult to employ. So if you have an operating system, you could plug this into a VM and kind of see if you can discover bugs that way, but it's very limited. Going the hardware route, well, this is hard because you have to kind of either acquire the equipment, which might be difficult to come by, or expensive. Even so, if you get some of this equipment, it's not really flexible for security purposes, so it's maybe more for testing or prototyping an actual implementation of something useful. And lastly, it's kind of hard to get handles on the USB protocol, and if you need to, well, if you'd like to kind of explore this in the security space, you need to know what's going on. So that can be quite a learning curve. So the question really is just, can we do better? Can we improve on the state-of-the-art kind of exploring the USB attack surface? And so existing solutions, I'm not going to go in depth into all of these, but they're really worth checking out. So early examples, using QEMU, put it in a VM and try to see what you can do with the USB software that's in this VM and change and modify the data that you're sending to it. The problem here is that you're kind of constrained to the implementation of emulating the USB protocol inside this VM. And so going the hardware route it provides a much more direct interface to kind of interact with the software. So I think one of the most successful approaches so far was Andy Davis in 2011 using a full-blown USB analyzer. So you have the man-in-the-middle capability between a host and device to see the data that's flowing across. And to fuzz it, well, we can modify this data, right? But what he had to do, and this was kind of, the problem with this approach is that it came with this proprietary software, and he had to go and actually interact with the GUI using a script in order to inject modified data, and this isn't ideal, right? So Arduino is another hardware device platform that was used to perform fuzzing, but it was a bit slow. Very recently, there's another approach using the BeagleBone, and this is also interesting. But I'm going to just talk a bit more about the face dancer, which was developed by Travis Goodspeed and Sergey Bretas, as mentioned. And what this device lets you do is emulate a given host or device. So the main drawback of this device is that you have to be able to feed the responses or the requests that you're interested in seeing played to the thing that you're fuzzing. So what I wanted was, I wanted a USB analyzer, but the problem is this thing's expensive, right? So this is $1,400. I'm a student. I'm in South Africa. I can't get my hands on this thing. But I could order a few face dancers. So kind of serendipitous, I ordered 2 to offset the high shipping costs of getting it to South Africa, and found out that I could actually use 2 usefully. The advantages of the face dancer as well, you have read and write ability on the USB communication port, but you need this knowledge, and it's not giving me that man-in-the-middle capability. So what is this USB fuzzing framework that I'm introducing? This transparent two-way emulation method. Well, it's a way to get man-in-the-middle capability. It's flexible because it's going to still allow you to use the software that the original face dancer uses to spoof your communication. It's cost-effective, much cheaper than your USB analyzer. And in the way that I've built it, you don't need to know what's going on the USB. Well, you don't need to know how to spoof those requests and data on the USB channel. All you need to be able to know is, well, you can see the data and you can learn from it, right? I'm going to go through some initial results that I found with the framework, and then the kind of avenues that this opens up in the USB fuzzing space as well. It's hard to prepare a talk in 15 minutes, and it's even harder fitting USB protocol into one slide, but I'm going to try my best. So if you really despise your weekends, I can recommend going through the USB spec. It's going to ruin it for you. So essentially, when you have a host and a peripheral communicating with each other, the host typically sends requests to the peripheral, and the peripheral responds with data in descriptors. So this would be an example request is the host asks the device, what type of device are you? What are your capabilities? How fast do you go? And the device would say, well, this fast, this is what I am. And device peripherals are divided into device classes, so you could have a keyboard, mass storage device, printer, and so forth. Importantly, there are endpoints dedicated to this data communication, and the endpoints designate the data direction and address between a peripheral and a device. And where data transfer is concerned, you have two types of transfers, control transfers and what I call non-control transfers. So control transfers are just the initial kind of startup phase where your host learns about your device. Non-control transfers refers to what your device is actually intended to do. So if it's a mass storage device, this is going to send the actual data that's on the USB stick. If it's a printer, it's going to be the channel that's used to send your document that's being printed. All of this communication is sent in packets consisting of an initial token, the actual data, and a handshake. Some of these communications don't actually have a data stage. I'll elaborate on that in a bit. So what's TWE about? Well, this lets you tap into this communication channel between host and peripheral. It lets you modify it. And the basic capability comes from the fact that with one phase dancer device, you can emulate both, well, either a host or a peripheral, but not both at the same time. If you have two, you can try to emulate both simultaneously. So would this idea work? And that's what this design is about, and it does work. So what's happened is that on your left side, you'll see a mass storage device, and on your right side, the host device. So when you initiate communication between a real host and a real device, the host is going to send a request. So I kind of coerce the host into sending me that initial request and do that with the peripheral emulation on your right. Once I have that request, I have it sent to the mediating computer. So the mediating computer is kind of negotiating between this real host and this peripheral. And I'll get that request. I'll emulate it back to the peripheral device using the host mode emulation on the second phase dancer. You'll note here there are some differences in the endpoint numberings and directions, and I'll revisit that later. And what I want to emphasize in this point is, yes, I use phase dancer devices. Yes, it's what Sergey and Travis built in the past, but it's not specific to this device. It's specific to having a USB controller with a microcontroller and some serial interface connecting to your man-in-the-middle computer. You can build this hardware yourself. It's not as if the framework depends on you buying a phase dancer, right? So to elaborate on the software implementation, you need two drivers on your mediating computer kind of handling this communication. So you have a host emulation mode driver and a peripheral emulation mode driver. And on the mediating computer, I just kind of communicate this data between them using named pipes. The two challenges encountered during this kind of building the system was there needed to be a way to handle endpoint mapping, and another issue was handshake emulation. That I can elaborate on if there's time, but it's just an optimization technique, so you could refer to the paper for that. With endpoint hijacking, so the issue here is when you have a peripheral, the endpoints on a peripheral are hard-coded. So when your device is ready to receive information from a peripheral, that peripheral tells it, I use in endpoints for data on endpoint 1, and that's it. And I use the out data channel on endpoint 2, and that's it. You can't change it. Unfortunately, on the phase dancer device, well, it's also got a USB microcontroller with hard-coded endpoints. So what you need to do is you need to map the endpoints from your real device to the one of the phase dancer, or otherwise it's not going to work. So what you'll see here is, on your left, the mass storage device might say, well, endpoint 2, out direction. And what I would do when this descriptor, so it's an endpoint descriptor containing this information, hits my mediating computer, I say, aha, I see it using endpoint 2 out, but my phase dancer in peripheral emulation mode can't use endpoint 2 out, so I'm going to just map everything from endpoint 2 out to endpoint 1 out. And the same for the in direction. So overcoming that and hijacking it in real time just lets you kind of do this transparent translation of destinations of the data. Okay, so initial results, just using this emulation method. We use the mass storage device. The idea here is just that you get the initial requests and responses. At some point, you hit this endpoint descriptor, you modify it, okay, it continues. You do everything necessary, and then once that's set up, you start receiving data on the other endpoints. So for a mass storage device, this will be SCSI data, and you'll be able to mount, read, and write using this information. So fuzzing results, what could I achieve with this framework so far? I used a really dumb fuzzing setup initially, so all I did was set up this host in peripheral emulation mode, plug in a device, let it run through the enumeration stage, maybe a little bit into the data stage for a few seconds, terminate it while flipping some bits. Obviously, maybe every fifth request or something like that, flip a byte or flip a bit here. And that would, I'd hope for the best and go to sleep, and next morning, do I have a new start screen? I don't know. So this was the kind of idea and what we ran into. So printer driver bug. This was basically a bug in popular operating system printer driver, and this is interesting because I don't think using the conventional techniques would have uncovered this, because what would happen was there was a certain bit that was flipped in such a way that it would change the control flow of the driver. So it would send different requests. And based on those requests, I would say not choose to acknowledge them. So just time out for that request, and it would send a repeated one. And then after that, send it some data, which it didn't expect in that state maybe, and that's what causes the crash. Another example is actually just freezing up an application. When you're in this application, you attempt to print, and it actually freezes it up, because if you're doing the emulation and you decide to not send the specific response in this case, what would happen is that this application would wait for it, and it wouldn't time out, and your whole application would essentially have a denial of service. Another example, a Wi-Fi dongle. So there are expected kind of standard responses to things like a clear feature in this USB protocol. And when you go and send something different, so a different value, maybe not 0, which would be the case in this instance, it causes a crash. So that's a type of bugs that we saw cropping up. I know I'm wafting over the details, but some of the stuff is still being disclosed and handled. So the point is just to say dumb fuzzing still works for this. There are many other applications, but this is what we have so far. So the limitations, well, it's slow. The problem is that doing this kind of back and forth with the requests and descriptors, it takes some time. Thankfully, USB as a protocol is fairly tolerant of delayed responses. So up to 500 milliseconds for most data transfers to occur. With this fuzzing framework, you get about 300 milliseconds average is what I found when I fuzz stuff. So that's about 300 milliseconds per packet that goes forth, request, and then response. What you could face, however, are device timeouts. So if a device has more stringent kind of requirements on timing, or a host or an operating system, you might actually hit those, and it might actually not work out for that device. So the other limitation, number of endpoints. I mentioned that we can do this endpoint hijacking scheme. The problem here is that if you have a USB device that has more than one out endpoint and more than two in endpoints, then that is beyond the ability of the face dancer. But what you'll find if you actually do this in practice is that most USB peripherals actually don't need more than that. For example, a mass storage device needs one in endpoint and one out endpoint. So in conclusion, well, it's flexible, it's inexpensive to use, and it does so effectively. So you can kind of have the capabilities of USB analyzer while being able to modify the software to your desires. So you just need a man-in-the-middle computer to kind of have the software running, and you just plug it in and you're off. No patching the host or the peripheral or the computer that you're using. Just some Python code running on that. And a nice benefit and side effect of this process is that you can record the whole communication exchange and replay it using just an emulator. So you just need one emulation device once you want to replay it. So related to that ability, for For example, so I mentioned here devices as seed files. So the idea is you can actually just use a peripheral as a seed file for fuzzing. Once you record some initial communication, maybe you do some stuff on a computer, open up your mass storage device, manipulate some files, you record all of that, and then you have that to replay. So this is kind of an idea to pursue, and maybe build up a database of devices as seed files, or even host behavior. And then one other idea that came out of this was in 2012, Milner had this idea of the talk-to attack at WOOT. And they basically swapped out the file system of a mass storage device in order to exploit this race condition on a smart TV. So why swap up the file system if you could just change the data in flight once you know you want to? So this is kind of an application that you could use the framework for. So that's the whole thing in a nutshell. I did put up some code on GitHub if you're really curious to check it out. I would not say it's ready for mass consumption, but in the interest of just having something to show for it, well, it's there. And I also just want to thank USENIX for the generous student grant, and thanks for being here. It's been great.
So how might a USB hub play into all of this?
So I've used the USB hub as a seed device as well, among other things. Using a USB hub with attached peripherals is going to create some complications. So you're probably not going to be able to get that information out of it using this framework quite yet. I wouldn't say it's a hardware restriction necessarily, but a software restriction. So you're going to have to build in some extra logic just to handle not dealing with the hub itself, but also a device attached to it. So there are some things in the protocol, right, that are going to, so the hub's going to communicate, okay, well, there's a device attached to me, and then you're going to have to kind of build that into the software logic.
In that case, I'll venture to inject my comment. It seems that what you're doing with the endpoint hijacking is network address translation. It's NAT in USB, essentially. So as the original presentation